Welcome to Designing with Position Sensors. In this video, you will learn about how automotive door handle designs benefit from various position sensing technologies. Automotive door handle systems are becoming increasingly more sophisticated with the advancement of deployable and flush door handles, especially in electric vehicles. In deployable door handle systems, it is important to accurately detect the position of the handle as it is extended, pulled, and retracted to ensure safety, proper operation, and a smooth user experience. In a magnetic-based implementation, as a motor extends the door handle outward, an embedded magnet rotates. A magnetic sensor detects the angle of rotation of the handle to stop the motor at the correct position and to detect when the user is pushing or pulling on the handle. Deployable door handles often come equipped with a passive entry system to recognize the key fob as the driver approaches the vehicle. However, soft touch detection is another option for presenting the handle should the user choose not to use passive entry. Capacitive sensors within the door handle can be used to detect hand proximity or a soft touch detection to deploy the handle. Finally, flap and fixed flush door handles incorporate a button press or soft touch detection to trigger the opening of the car door. An applied force slightly deflects a metal target within the handle, moving the target closer to an inductive sensor and allowing the inductive touch to be sensed. This same inductive touch button technology can be used for button press detection in door keypads and push buttons, as well as automotive trunk release systems. The ability to detect whether the door is open or closed is also key to keeping the driver, passengers, and vehicle safe. A magnet embedded in the door frame, paired with a Hall effect switch to detect the presence of the magnetic field, allows for simple door open-close detection. The long-term reliability of door handle systems stems in part from the contactless methods of implementing the sensing requirements above. The contact-free implementation reduces wear and tear compared to traditional mechanical implementation, thereby increasing product lifetime and providing a polished user experience. TI's position sensing portfolio provides several types of devices for automotive door handles, which include AMR magnetic sensors, Hall effect magnetic sensors, capacitive sensors, and inductive sensors. The TMAG6180Q1 is an automotive high-precision analog AMR angle sensor with a 360-degree angle range thanks to integrated quadrant detection using Hall sensors. Its ultra-low latency and differential analog sine and cosine outputs allow for fast and precise angle calculation for deployable door handles. The TMAG6180Q1 is functional safety compliant with documentation to aid ISO 26262 system design up to ASIL B. The TMAG5131Q1 is an automotive low-power, low-voltage, omnipolar Hall effect switch. The device is available with push-pull or open-drain output options and features a high-precision magnetic thresholds for door open and close detection. The FDC1004Q1 is an automotive 4-channel, 16-bit capacitance to digital converter with an active shield driver. The input range of plus or minus 15 picofarads, extendable to a range of 0 picofarad to 115 picofarad, measurement resolution of 0.5 femtofarads, and programmable output rates make it suitable for hand proximity or soft touch detection. The FDC1004Q1 is AEC Q100 Grade 1 qualified with HBM ESD classification level 2 and CDM ESD classification level C5. The LDC3114Q1 is an automotive 4-channel inductance to digital converter for low-power proximity and touch button sensing. The device's robust EMI performance allows CISPR 22 and CISPR 24 compliance. Button mode enables button press detection with baseline tracking and advanced on-chip post-processing. Configurable scan rates and low current consumption make the device suitable for soft touch or button press detection. The LDC3114Q1 is AEC Q100 Grade 1 qualified with HBM ESD classification level 2 and CDM ESD classification level C4B. A replica door and handle were designed and 3D printed to demonstrate a deployable door handle, soft touch detection, and door open-close detection. An arm attachment connects to a DC gear motor via a coupler. The gear motor is driven by a DRV 8220 motor driver. The motor arm presses on the center bar of the handle to extend the handle outward. When the motor arm retracts, a pair of 3D printed springs center the handle back to its home position after being pressed or pulled. A diametric cylinder ring magnet is embedded in the handle beside the TMAG 6180Q1 AMR sensor, which is placed in an on-axis position to minimize amplitude mismatch and achieve good angle measurement linearity. The TMAG 6180Q1 detects the magnet's rotation and therefore the handle position as the handle moves or as the user is pulling or pushing on the handle. Another magnet is embedded in the bottom of the door frame. A TMAG 5131Q1 Hall effect switch mounted on the door above the magnet senses when the door is opened or closed. An FDC 1004Q1 measures the capacitance of two different sensors made of layered copper tape. One sensor is located on the back of the door handle for hand proximity and soft touch detection. Another sensor is behind a capacitive touch button on the door, demonstrating another instance of soft touch detection. First, let's look at the door and door handle in the initial position, along with the outputs of the TMAG 6180Q1. The analog sine and cosine outputs from the TMAG 6180Q1 are used in an arctangent 2 calculation to show the angle that corresponds to the home position of the door handle, and the two digital quadrature outputs extend the angle range of the AMR sensor to 360 degrees. When the user presses the door handle, the TMAG 6180Q1 detects the small change in angle as shown in the plot below. In this demo, the small angle change is one condition that must be met to deploy the door handle. The other condition involves the capacitive sensor, which we will discuss momentarily. When both conditions are met, the motor drives the handle out and stops at a precise angle configured in the MCU. The TMAG 6180Q1 also detects changes in the angle as a result of the handle being pulled, so the handle will not inadvertently retract on the user's fingers. The handle is programmed to retract after 3 seconds as long as the user's hand is not present. The TMAG 5131Q1 detects when the device is near the magnet on the door frame. When the door is closed, the device senses the magnet and the output is asserted low. When the door is fully open, the device does not sense the magnet, which causes the output to be asserted high and the door open icon toggles. This motion was simulated during prototyping using TI Magnetic Sense Simulator, TIMS, to confirm magnet placement and expected operation of the TMAG 5131Q1. Now, let's look at how the FDC 1004Q1 enables soft touch detection for deploying the handle. The pre-programmed configurable thresholds for each of the capacitive sensors on the handle and the side button are shown. A gentle press on the handle leads to a change in capacitance, which triggers the extension of the handle. A gentle touch of the side button also shows the same functionality. Notice that the handle sensor also allows the FDC 1004Q1 to detect when the user's hand is pulling on the handle, helping to ensure the handle doesn't retract on the user's fingers. Inductive touch is not included in this demo, but can be easily implemented as a touch button or in the door handle itself. Inductive touch may be more suitable for specific use cases or door handle types, such as flap flush or fixed flush door handles, keypads and push buttons, or trunk release systems. To help in your automotive door handle designs, here are some recommended position sensing resources. The TI Magnetic Sense Simulator, TIMS, can provide insight into optimal magnet selection and placement for magnetic-based position sensing systems. The TMAG 6180Q1 datasheet and TMAG 6180-6181 EVM allow evaluation of the TMAG6180Q1 AMR sensors for fast and precise angle measurements. FDC 1004, Basics of Capacitive Sensing and Applications, covers the basics of capacitive sensor design and outlines different capacitive sensor topologies. Inductive Touch, Configuring LDC2114 and LDC3114 touch button sensitivity, describes the working principles for inductive touch buttons and explains how to configure the button activation force for these devices. Inductive Sensing Calculator Tools assists with coil design and device-specific configurations for LDC devices. Thanks for watching, and please visit ti.com/AMR, ti.com/Hall-Effect, ti.com/Inductive, and ti.com/product/FDC1004Q1 to find more resources and tools.